The universe is not a collection of isolated islands. It is a single, breathing organism. Its galaxies are bound together by vast, invisible threads of dark matter and gas, forming the largest structure in existence. This is the cosmic web, and it holds the master blueprint for everything we see in the night sky. By the end of this exploration, you will understand the hidden architecture that dictates the fate of every galaxy, including our own. We will uncover how astronomers found this invisible framework, the cutting-edge tools mapping its form, and why its discovery forces us to rethink our cosmic address. How does it feel to know you are part of a structure spanning billions of light years? For most of human history, the stars above seemed like a beautiful, random scattering. Ancient astronomers mapped constellations, but the spaces between them felt like a dark and formless ocean. This view of a fundamentally chaotic cosmos persisted for centuries, even as our telescopes grew more powerful. We saw more stars, more galaxies, but they still appeared as lonely islands in a vast, empty sea. Then, in the final decades of the 20th century, something changed. Astronomers embarked on a monumental new task, not just looking at individual galaxies, but counting them, cataloging their positions across immense stretches of space. They began creating three-dimensional maps of the cosmos, and when they stepped back to look at these maps, the random scatter dissolved. A breathtaking pattern emerged. Galaxies were not scattered evenly at all. They were arranged in immense, interconnected walls spanning hundreds of millions of light years. They clustered along delicate, thread-like filaments. And between these structures lay enormous, terrifyingly empty regions, cosmic voids so vast they could contain thousands of galaxies, yet held almost none. This was the moment our understanding of the universe fractured and reassembled. We did not live in a formless chaos. We lived inside a single, coherent structure, an architecture of staggering scale and beauty. This structure had a name, the large-scale structure of the universe, and its blueprint was the cosmic web. The force that drew this blueprint over nearly 14 billion years was the relentless, patient pull of gravity. It began with the tiniest imperfections in the infant universe, slight ripples in density. Over cosmic time, gravity amplified these ripples. Matter began to flow, streaming along invisible channels, pooling at the intersections. What started as a near-uniform soup of particles slowly, inexorably, sculpted itself into a web of filaments, nodes, and voids. This shift in perspective is profound. It means our Milky Way galaxy is not drifting aimlessly. It is following a highway laid down at the dawn of time, a thread in the grand tapestry. Understanding this architecture, this shift from apparent chaos to hidden order, is the very first step to finding our true place in the cosmos. Gravity is the most patient artist in existence. Its canvas is the fabric of space and time itself, and it has been working on this single masterpiece for over 13 billion years. But every great sculpture begins with a rough sketch, a faint outline in the stone. For the cosmic web, that initial sketch was drawn in the first fleeting moments after the Big Bang, on a scale so small it defies comprehension. The universe was a seething, hot, nearly uniform soup of energy and particles. Yet even in that perfect uniformity, there were whispers of difference, tiny quantum ripples in density. Think of the surface of a perfectly still pond, but at the subatomic level, it is never truly still. It flickers with inherent, unpredictable vibrations. Those primordial flickers were frozen into the fabric of the expanding cosmos, imprinted like a cosmic fingerprint. This is the astonishing part. Those infinitesimal ripples, fluctuations so slight they would be unnoticeable in any room, held the entire future blueprint of the universe. Gravity saw them, In regions where the density was just a fraction higher, gravity had a tiny bit more to work with. It began its slow, relentless pull, attracting the sparse matter around it. Over millions, then billions of years, this process snowballed. More matter gathered, which meant stronger gravity, which pulled in even more matter. These regions became the dense knots and intersections of the cosmic web, the future homes of immense galaxy clusters where thousands of galaxies swarm together. Meanwhile, the opposite was happening in the regions that started with slightly lower density. As matter was pulled toward the growing knots, these areas were slowly drained. They became the cosmic voids, those staggering empty bubbles in the web that can span hundreds of millions of light years, containing almost nothing. This gravitational tug of war, the flow of matter from the voids into the filaments and finally into the dense clusters, is the fundamental force that wove the entire cosmic tapestry. But here lies a profound mystery. When astronomers calculated how much gravity was needed to sculpt the web we see, to pull galaxies into filaments and clusters with the speed we observe, they came up short. The visible matter, the stars and galaxies and gas we can see, accounts for only a small fraction of the required force. Something invisible was providing the bulk of the gravity, an unseen hand guiding the architecture. This realization pointed to the existence of the most elusive, the most mysterious material in the cosmos, a shadow framework holding the luminous web together. This invisible framework has a name: dark matter. It is the ghost in the cosmic machine, the unseen force whose signature is written everywhere in the behavior of the universe we can see. The evidence for its existence began not with a sighting, but with a profound mismatch, a cosmic accounting error. In the 1970s, astronomer Vera Rubin was studying how spiral galaxies rotate. By measuring the speed of stars at different distances from a galaxy's bright center, she expected to see a pattern. Stars farther out, feeling the weaker gravitational pull of the distant core, should orbit more slowly, just as Pluto moves more sedately around the Sun than Earth does. But the data told a different story. Stars at the very edges of galaxies were whipping around just as fast as those near the center. It was as if the entire galaxy was embedded in a massive, invisible sphere of gravity, a halo of something that did not glow. The visible galaxy was just the bright tip of a vast, dark iceberg. This was the first strong clue that most of the matter holding galaxies together was completely unseen. Another line of evidence comes from a phenomenon called gravitational lensing, where the gravity of a massive object bends the very fabric of space-time, warping the light from objects behind it like a cosmic magnifying glass. When astronomers look at massive galaxy clusters, they often see stretched and distorted images of distant galaxies arcing around the cluster's edges. But when they calculate how much visible mass is in the cluster to cause that bending, the numbers do not add up. The gravitational lens is far too strong. There must be an enormous amount of invisible mass, dark matter, permeating the cluster and providing the extra gravity. We now understand that this dark matter forms the skeleton of the cosmic web. It clumped first under gravity's pull, creating an immense three-dimensional scaffolding that stretched across the young universe. Its gravitational wells became the blueprint. Ordinary matter, the atoms that make up stars, planets, and us, was then drawn along these pre-existing channels. It flowed into the dark matter filaments, igniting into galaxies at their intersections. So when we map the great walls and threads of galaxies, we are not mapping the primary structure. We are tracing the luminous highlights along a shadow architecture. The glittering cities of the cosmos are built along highways we cannot see, following a map drawn in invisible ink. This raises an inevitable and thrilling question. If dark matter's gravity shapes everything, and we can only see its effects, how do we possibly begin to chart the form of this ghostly web itself? the dark matter scaffold was in place, a silent and invisible framework stretching across the cosmos. But a skeleton alone does not make a living being. It needs flesh, blood, and a beating heart. For the cosmic web, that vitalizing element is the ordinary matter we know and are made of, the protons, neutrons, and electrons that form every star, planet, and person. This is the second beautiful principle of the web's creation. Baryonic matter, as scientists call it, is not the architect. It is a follower, drawn into a dance choreographed long before it arrived. Think of a powerful magnet hidden beneath a sheet of paper. If you sprinkle iron filings onto that paper, they do not fall randomly. They instantly align themselves into graceful, curving lines, tracing out the shape of the magnetic field that is completely invisible to your eye. The dark matter filaments are that hidden magnetic field on a cosmic scale. For hundreds of millions of years after the Big Bang, the universe was far too hot and energetic for atoms to form. It was a thick, opaque fog of charged particles, but as expansion cooled the cosmos, a pivotal moment arrived. Electrons combined with protons, forming the first neutral hydrogen atoms. The cosmic fog cleared, and for the first time, light could travel freely. In that newly transparent universe, the ordinary matter, now simple gas, could finally feel the gentle, persistent tug of the dark matter's gravity. It began to flow. Vast rivers of primordial hydrogen and helium gas were funneled into the gravitational valleys of the dark matter filaments. They streamed along these invisible channels, converging at the intersections where filaments crossed. At these cosmic crossroads, the density became immense. As the gas piled in, it collided, compressed, and began to heat up through the sheer force of gravity. But then, something miraculous happened. Through complex processes, this superheated gas was able to cool, condense, and fragment. Within these dense, cooling knots, the first stars ignited. Their brilliant light pierced the darkness of the early universe. These were not isolated stars. They were drawn together by their shared origin in the flow, becoming the first proto-galaxies. This is why galaxies are not scattered randomly like confetti. They are strung along the filaments of the web like luminous pearls on a dark string, and they gather in brilliant, dense clusters at the nodes where the strings tie together. Our own Milky Way resides on a local filament, part of a smaller web within the greater one, slowly being drawn toward the immense gravity of the Virgo cluster. We are following a river of gas and stars that began flowing over 13 billion years ago. This principle solves the mystery of galactic placement. But it presents a new, tantalizing challenge. If the luminous galaxies trace the web's outline, how do we see the web itself, the vast, dark filaments that stretch between the glittering nodes? The answer lies in finding the ghostly glow of the gas that never became a star. The luminous galaxies give us the outline, but the true filaments themselves remained shrouded in darkness, vast and seemingly empty. To map the unseeable, astronomers had to become cosmic cartographers, inventing ingenious new ways to see with gravity and light. Their first great tool was a census of unprecedented scale. Projects like the Sloan Digital Sky Survey did not just take pretty pictures of the sky. They systematically measured the light from millions of galaxies, capturing a specific clue in their starlight. As the universe expands, light from receding galaxies is stretched toward the red end of the spectrum. By measuring this redshift, astronomers can calculate not just where a galaxy is on the sky, but how far away it is. This transforms a flat image into a three-dimensional map. Imagine knowing the exact street address of millions of homes across an entire continent. When you plot them all in 3 dimensions, the shape of the cities, the highways connecting them, and the empty countryside between them becomes stunningly clear. That is what these redshift surveys revealed. The Sloan map showed the universe in a cube a billion light-years on a side, with galaxies arranged in delicate, interconnected sheets and filaments surrounding immense dark voids. It was the first direct observational proof of the Webb's architecture, but these maps only showed where the galaxies were. The filaments between them were still dark on the survey images. To find the hidden material within the filaments themselves, scientists turned to cosmic lighthouses. They used quasars, the incredibly bright cores of distant galaxies, powered by supermassive black holes. As a quasar's light travels billions of light years to reach us, it passes through the faint, diffuse gas that fills the cosmic web. That gas absorbs very specific colors from the quasar's brilliant beam. When astronomers break the quasar's light into a rainbow-like spectrum, they see a forest of dark absorption lines. Each line is like a fingerprint, a chemical signature of a cloud of hydrogen gas the light passed through. By studying this Lyman alpha forest, as it is called, scientists can detect the tenuous gas that never collapsed into galaxies. They can trace its distribution along the line of sight, building up a profile of the invisible material threading the cosmos. It is like using a distant spotlight to illuminate the fine mist between the trees in a vast, dark forest. Alongside these observations, a parallel universe was being built inside supercomputers. Projects like the IllustrisTNG simulations start with the known laws of physics and the initial conditions of the early universe. They then simulate the evolution of both dark and ordinary matter over billions of years in a virtual cube of space. Watching these simulations run is like watching a time lapse of the universe itself. You see the dark matter condense into a delicate cosmic spiderweb. You watch gas flow along the filaments, igniting into galaxies at the nodes. The final snapshot looks almost identical to the maps from the Sloan survey. These simulations are not just pretty animations, they are crucial testing grounds. They allow scientists to ask what-if questions. What if dark matter behaved slightly differently? What if the early universe had more ripples? By comparing the simulated web to the observed one, they can refine our understanding of the fundamental rules that built everything. Together, these tools, the galaxy censuses, the quasar backlights, and the digital universes, are weaving the first true maps of the cosmic web. They reveal a structure of such grandeur it defies human scale. Yet, for all this progress, a haunting question remains. If we are embedded in this web, flowing along its currents, where exactly is it taking us? What is the ultimate fate of our galactic neighborhood within this immense architecture? A single thread of the cosmic web is not a simple, taut string. It is a river system on a galactic scale, a braided channel of gravity through which the raw material of creation continuously flows. To understand its anatomy, we must zoom in from the grand map to a local neighborhood, to the filament our own Milky Way calls home. Within these vast structures, the space between galaxies is not truly empty. It is filled with an elusive, incredibly diffuse form of matter known as the warm-hot intergalactic medium, or the WHIM. This is a thin plasma, a gas so hot it has been stripped of its electrons, yet so spread out it would feel like a better vacuum than anything we can create on Earth. For decades, this material was the universe's missing Baryon problem, a huge portion of ordinary matter that theory said must exist but observations could not find. It turns out it was hiding in plain sight, woven into the very fabric of the filaments themselves. This WHIM is the lifeblood of the cosmic web. It is the reservoir from which galaxies drink to fuel the birth of new stars. Over cosmic time, this hot, thin gas slowly drains from the filaments, pulled by gravity into the waiting galaxies strung along its length. But the filament's influence is more than just a passive gas pipeline. Its immense gravitational field acts as a cosmic guide rail. Studies of thousands of galaxies within filaments show a fascinating pattern. Their rotations are often aligned with the filament's axis, like logs floating down a river, all pointing in the same direction. Furthermore, their trajectories are not random. Galaxies move along these dark matter highways, often flowing toward the massive clusters at the intersections. This means a filament is not a static sculpture. It is a dynamic, flowing conduit. It directs traffic, shapes spin, and feeds its inhabitants. For a galaxy like our own, living within such a structure is a fundamental part of its life story. The gas that will become future stars is still arriving, funneled along this ancient route. Our motion through the local web is not a lonely voyage, but part of a vast, coordinated migration. This microscopic look transforms our view from architecture to ecology. The cosmic web is not just a map of where things are. It is a description of how they live, move, and grow. If the filaments are the rivers, then the dense clusters at their intersections are something else entirely, the cosmic equivalent of sprawling, gravitational metropolises. Yet within this cosmic ecology, the most profound spaces are defined by absence. The voids of the cosmic web are not simply the leftover gaps. They are the foundational negative space that gives the entire structure its breathtaking, three-dimensional form. If the filaments are the great rivers of matter and the clusters are the bustling cities, then the voids are the continents of near-nothingness, the immense spherical bubbles that make up the bulk of the universe's volume. Each one can span a staggering 300 million light-years or more, a region so vast it could contain thousands of galaxies like our own, yet holds only a handful of lonely, isolated island galaxies drifting in the dark. This profound emptiness is not a vacuum in the earthly sense. Even these voids are threaded with the faintest traces of the warm, hot intergalactic medium, that elusive WHIM, and they are populated by a sparse population of dark matter. But their density is so incredibly low that they exert a different kind of influence. They act as cosmic pressure chambers. The relentless gravitational pull from the surrounding walls and filaments of the web squeezes inward on these underdense regions, sculpting them over billions of years into roughly spherical shapes. Picture a cluster of soap bubbles clinging together. The delicate walls of the bubbles are under tension, pushed into curved forms by the empty space inside them and the pressure from their neighbors. The cosmic web operates on a similar principle, but with gravity as the sculptor and the voids as the bubbles. This relationship is what creates the foam-like structure we observe. The web is defined as much by where matter is not as by where it is. The glittering filaments and brilliant clusters are the walls of this cosmic foam. Their very existence and sharp definition rely on the contrasting emptiness that borders them. Without the voids pushing inward, the filaments would not be pulled so taut. Without the immense gravitational slopes leading from the empty centers of voids up into the dense walls, matter would not flow so efficiently. These vast regions of absence are therefore active players in the cosmic story. They are the engines of a large-scale flow, as galaxies on the edges of voids feel the gentle but persistent tug from the denser regions beyond, slowly migrating out of the emptiness and toward the web's luminous threads. So when we look at a map of the large-scale structure, we must train our eyes to see not just the bright knots and strings, but the majestic, spherical voids between them. They are the silent, dominant architecture. Their emptiness is what gives the light its meaning, and their gravitational influence choreographs the slow, grand migration of galaxies across the eons. This understanding of the web as a balanced system of presence and absence leads us to a final, pivotal question. If this structure dictates the motion of galaxies over billions of years, what ultimate destination does it have in mind for our own celestial home? Our galaxy's journey is not a solitary drift. It is part of a grand, coordinated migration. For decades, astronomers have known that all galaxies are receding from each other as the universe expands, a motion described by Hubble's law. But when they looked closer, they noticed something peculiar. Our entire local group of galaxies, along with our neighboring clusters, is moving sideways against this universal backdrop at a staggering speed of over 2 million kilometers per hour. It is as if we are caught in a vast, invisible river current flowing in a specific direction. This is a bulk flow, a coherent motion of immense structures, and it pointed to a profound gravitational mystery. The source of this pull was traced to a region of space in the direction of the constellation Centaurus, an area astronomers dubbed the Great Attractor. The name conjures images of a single, monstrous, hidden object, a cosmic siren pulling everything toward it. But the truth is far more fascinating and speaks directly to the power of the cosmic web. The Great Attractor is not a lone, dark giant. It is a gravitational focal point, a dense knot in the tapestry created by the combined mass of an entire complex of superclusters, a convergence of several massive filaments of the cosmic web. Our motion is not toward a thing, but toward a place, a gravitational valley so deep that its pull dominates our local universe. This region, known as the Laniakea supercluster, is our true cosmic continent. It contains over 100,000 galaxies, all bound by this shared gravitational destiny, all flowing toward the same central basin. The Great Attractor is simply the densest, most massive part of that basin. This discovery fundamentally changed our understanding of cosmic motion. It showed that the expansion of the universe is not the only force moving galaxies. Superimposed upon that smooth, outward stretch are these powerful, local currents, these bulk flows, generated by the uneven distribution of matter on the largest scales. We are not just expanding, we are surfing the gravitational waves of the cosmic web, drawn along by the integrated pull of structures so vast they bend the paths of entire galaxy clusters. This reveals the web not as a static map, but as a dynamic force, an active conductor of the universe's largest orchestrations. If the web's gravity can steer us so decisively, what other invisible currents might it be directing, and what does this tell us about the ultimate fate of everything caught in its flow? These cosmic currents do more than just move galaxies, they sustain them. The filaments of the web are not inert roads, they are the life-giving arteries of the universe, the very source from which galaxies draw their breath and build their stars. For a galaxy to thrive, it needs a continuous supply of fresh, cool gas, the raw hydrogen fuel for new stellar furnaces. But for a long time, astronomers faced a puzzle. In the dense, violent environments of galaxy clusters, the gas between galaxies is heated to millions of degrees by shock waves and collisions. This superheated plasma is difficult for a galaxy to capture and cool down, making it a poor fuel source. This hot mode accretion is like trying to drink from a geyser. It is turbulent and inefficient. So how did galaxies, especially majestic spirals like our own Milky Way, acquire enough cool gas to build their vast, star-filled disks? The answer lies in the quiet, dark channels of the cosmic filaments themselves, through a process called cold flow accretion. Imagine a galaxy sitting at the intersection of several dark matter filaments. While the space around it might be filled with hot, thin gas, the dense cores of those filaments are protected. They act as insulated pipelines, carrying reservoirs of much cooler, denser gas directly from the intergalactic wilderness. This gas streams along the filament, following the gravitational contour like a river down a mountain valley, and flows directly into the galaxy's extended dark matter halo. Crucially, it does so without being shock-heated to extreme temperatures. It arrives as a cool, dense river, ready to sink toward the galaxy's center, condense, and ignite into new stars. This is the galaxy's umbilical cord. In the early universe, a growing spiral like the Milky Way was likely fed by several of these cold streams simultaneously, each one funneling pristine gas from a different filament of the web. These rivers of cold gas provided a steady, rich diet that allowed our galaxy to build its disk and maintain star formation across billions of years. The history of a galaxy, its size, its shape, and its stellar population, is fundamentally written by the number and strength of the filaments that nurtured it. A galaxy fed by a single megastream might become a small, anemic dwarf. A galaxy like ours, sitting at a richer intersection, was gifted multiple robust streams, enabling it to grow into a grand spiral. This transforms our view of the cosmic web from a mere map of gravity into a story of cosmic ecology. The filaments are not just scaffolding, they are the roots of a galactic tree, drawing nourishment from the soil of the universe to feed the brilliant blossoms of stars. But this nourishment does not last forever, and the environment a galaxy inhabits within the web determines its ultimate fate. The cosmic web is not just a map of location, it is a powerful predictor of galactic destiny, shaping not only where a galaxy goes but what it becomes. The principle is elegantly simple, yet its consequences are written across the night sky in two distinct types of galaxies, spirals and ellipticals. A galaxy's morphology, its very shape and future, is largely dictated by its address within the cosmic architecture. Consider a galaxy living a relatively quiet life along a filament like our own Milky Way. It receives a steady, regulated diet of cool gas from its dark matter pipeline. This allows for orderly, sustained star formation. New stars are born primarily in the spiral arms, their brilliant blue light a sign of youth and vitality. The rotation of the disk is preserved, and the galaxy maintains its elegant pinwheel structure. This is the life of a spiral galaxy, a story of gentle growth and continuity, made possible by its position on a cosmic backroad. Now picture a galaxy that has migrated to the heart of a dense cluster, a massive node where multiple filaments converge. This environment is a gravitational metropolis, a place of constant traffic and colossal forces. Here, galaxies move at tremendous speeds, passing perilously close to one another. The thin, hot gas that fills the space between them in the cluster acts like a fierce wind. As a galaxy plunges through this intracluster medium, this wind violently strips away its precious reservoir of cool gas in a process called ram pressure stripping. It is like driving a convertible through a torrential downpour. The galaxy's fuel supply is ripped right out of its grasp. Furthermore, in these crowded quarters, galactic collisions and mergers are frequent. When two spiral galaxies merge, their beautiful, ordered disks are utterly destroyed in a gravitational dance of chaos. The gas clouds within them collide, triggering a final, furious burst of star formation that quickly consumes the remaining fuel. The result is not a larger spiral. It is an elliptical galaxy, a smooth, featureless sphere or egg of mostly old red stars, with its gas supply gone, either stripped by the cluster wind or exhausted in the merger firestorm. New star formation grinds to a halt. Astronomers call these red and dead galaxies, their stellar populations aging in unison without the blue spark of newborn stars. Their spiral structure, the signature of a quiet, fed existence, is erased forever. This is the transformative power of the web's environment. The filament offers a path of sustained life, while the cluster node presents a destiny of dramatic interaction and ultimate stillness. Our Milky Way's spiral form is a direct testament to the quieter suburban lane it has traveled along for billions of years, but this too is changing. We are on a slow migration toward the dense Virgo cluster, pulled by the same web currents we have discussed. In the distant future, our local filament may deliver us into that more violent urban core, setting the stage for a far more dramatic chapter in our galaxy's life story. The cosmic web, therefore, holds the script. It writes the conditions that determine whether a galaxy will shine with the blue light of continuous creation or settle into the red glow of a quiet, aging retirement. This grand flow of matter through the cosmic web hides a profound mystery, one that has puzzled cosmologists for decades. When scientists calculate how many ordinary atoms, the protons and neutrons known as baryons, should exist based on the echo of the Big Bang, the numbers tell a clear story. Yet for years, our telescopes could only find about half of that predicted matter in the stars, galaxies, and glowing gas clouds we could see. It was a cosmic accounting error of epic proportions. Where was the other half of the normal stuff in the universe? The prime suspect for this missing matter was hiding in plain sight, woven into the very fabric of the filaments we have been exploring. This is the warm-hot intergalactic medium, the WHIM. It is a ghostly plasma, a gas so hot its atoms are stripped bare, yet so fantastically diffuse it is nearly intangible. Imagine the air in this room, then spread a single breath of it across a volume the size of our entire solar system. That is the staggering emptiness we are talking about. Detecting something so thin and so hot is a monumental challenge. It does not glow in the familiar light of stars. Instead, it whispers its presence in the far ultraviolet and X-ray parts of the spectrum, wavelengths that are completely blocked by Earth's protective atmosphere. To find it, we must send our eyes into space. Observatories like the Hubble Space Telescope and the Chandra X-ray Observatory act as cosmic detectives. They search for the subtle fingerprints this tenuous gas leaves on the light of distant quasars, or they try to capture its own faint, diffuse X-ray glow where filaments are most densely packed. Every faint signal they gather is a clue, helping us trace the outline of this elusive material. Finding the WHIM is about more than just balancing the universe's books. It is about closing the loop on the greatest story of all, the complete cycle of matter from the first moments of creation to the present day. This missing matter is the reservoir, the intermediate state between the primordial hydrogen forged in the Big Bang and the stars and planets that eventually form. It is the cosmic circulatory system, the blood flowing through the arteries of the web. By finally mapping it, we are not just finding what was lost. We are witnessing the connective tissue of the cosmos itself, the medium through which the universe continually reshapes and renews itself. The hunt for the missing matter demanded a new kind of vision, one that could see the faintest whispers of heat in the darkest corridors of space. For decades, the warm-hot intergalactic medium was a compelling theory, a mathematical necessity hiding in the gaps of our cosmic maps. To turn this ghost into a reality, astronomers needed to build eyes that could perceive the universe not in starlight, but in the language of extreme energy. They turned to the high-energy spectrum, to X-rays. In the silent vacuum of space, observatories like the Chandra X-ray Observatory and XMM Newton began a patient search. They focused their gaze on the spaces between massive galaxy clusters that were suspected to be connected by a thick filament of the cosmic web. They were looking for a specific signal, the faintest glow of X-ray emission from gas heated to millions of degrees. This was not about seeing a bright object. It was about detecting an almost imperceptible haze, a cosmic fog so thin its light is drowned out by everything else. After years of painstaking observation, they found it, in the filament bridging the colossal Abell 2220 and Abell 2221 galaxy clusters. Chandra detected the telltale X-ray signature. It was the first direct image of the hot gas within a cosmic web filament, a monumental breakthrough. Here was the long-sought WHIM, not as an abstract line in a quasar's spectrum, but as a vast physical structure glowing in a light invisible to human eyes. This was seeing the skeleton of the universe begin to glow with its own ethereal light. Yet, X-rays only tell part of the story, mapping the hottest, densest parts of the gaseous web. To trace its more tenuous outskirts, astronomers devised an even more ingenious method, using the most fleeting and powerful flashes in the cosmos as their tool. They turned to fast radio bursts. These enigmatic events release more energy in a millisecond than our sun does in 3 days, and their brief, brilliant signals travel billions of light-years to reach us. As a fast radio burst's light races through the cosmic web, it interacts with the free electrons in the WHIM. This interaction is subtle but measurable. It causes a delay, a dispersion, where lower frequency radio waves arrive slightly later than the higher frequencies. By precisely measuring this dispersion delay, scientists can calculate the total number of electrons the signal encountered along its path. It is like timing how long it takes different colors of light to travel through a frosted glass window. The thicker the frost, the greater the delay. Each fast radio burst acts as a single, brilliant flashlight beam, illuminating a narrow needle through the cosmic haystack. By combining the paths of many bursts from different directions, astronomers can begin to build a statistical map of the WHIM density throughout the vast volumes of space. We are now crossing a frontier where theory becomes observation. The invisible filaments are slowly coming into view, not as lines drawn on a simulation, but as tangible reservoirs of million-degree plasma mapped by X-ray glow and probed by cosmic flashes. This is more than finding missing atoms. It is watching the universe's circulatory system pulse with its own faint, fiery light. To see the cosmic web in its infancy, we must look back over 13 billion years to a time when the universe was a simpler, darker, and far more chaotic place. The grand architecture we see today did not spring forth fully formed. Its foundations were laid with astonishing speed in the first few 100 million years after the Big Bang. In that primordial darkness, the dark matter had already begun its work. The subtle ripples from the universe's birth had amplified just enough for gravity to start sculpting the very first tenuous filaments of the cosmic web. This was the universe's first skeleton, a delicate network of dark matter threads woven into a space that was still small enough, dense enough for everything to be connected. Within this shadowy scaffold, the first ordinary matter, pure hydrogen and helium gas, began to move. It was drawn into the shallow gravitational valleys of those nascent filaments, starting a flow that would continue for billions of years. But here, in the infant cosmos, everything was closer together. The densities were higher, the gravitational tugs stronger, and the gas flowed along these dark pathways at a ferocious pace. This was not the stately, ordered universe we see today. It was a frenetic construction site operating at a scale and speed we are only beginning to comprehend. The critical evidence for this early web comes from our most powerful time machines, telescopes like the James Webb Space Telescope. By staring deep into cosmic dawn, Webb is revealing a universe that defied our expectations. It is finding galaxies that are brighter, more massive, and more numerous than our models predicted for such an early epoch, and they are not scattered randomly. Even at these incredible distances, when the universe was less than 5% of its current age, these primordial galaxies show a tendency to align. They appear in faint, linear arrangements strung along like beads on a string that we cannot yet see. These alignments are the ghostly imprints of the earliest cosmic filaments. They tell us the Webb's framework was not a late development. It was the very first large-scale structure to emerge, the initial mold into which the first luminous matter was poured. Within this denser, more dynamic web, the conditions were perfect for cosmic extremes. The rapid inflow of gas along the filaments created regions of incredible density at their intersections. Here, the first stars, known as population 3 stars, could form. These were behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying young in spectacular supernova that seeded the cosmos with the first heavy elements. The same inflows also fed the growth of the very first supermassive black holes, which astronomers now believe formed concurrently with their host galaxies, feasting on the abundant gas delivered by the Webb. This ancient, bustling web set the initial conditions for everything that followed. The distribution of those first galaxies, the enrichment of the early gas with new elements, and the placement of the first black holes were all dictated by the pattern of those first filaments. The universe we inhabit today, with its majestic spirals and glittering clusters, is the mature, expanded, and evolved version of that frantic, foundational blueprint. The web was there at the beginning, quietly conducting the first movements of the cosmic symphony. The cosmic web is not a frozen monument. It is a living, breathing entity, constantly reshaping itself in a slow-motion dance of unimaginable scale. This is the fifth principle, the dynamic and evolving nature of the structure that cradles us. The grand filaments we map are not permanent highways. They are rivers that can change their course, merge with tributaries, or even dry up over the eons. This evolution is driven by the relentless gravitational pull between the web's densest parts. When two massive galaxy clusters, each the nexus of many filaments, begin to fall toward one another, the entire local architecture warps. The filaments connecting them thicken with the influx of new matter, becoming gravitational superhighways. In a dramatic collision, those filaments can be violently twisted, severed, and rewired, redistributing the cosmic traffic of galaxies into a new configuration. Simultaneously, the voids between these structures are not passive. As the universe expands and matter continues to drain from the voids into the surrounding filaments, these empty regions grow ever larger and more spherical, their boundaries becoming sharper. The web is a tug of war between congregation and emptiness, a process that never stops. All of this change unfolds against the backdrop of the universe's most dominant force, its accelerating expansion. This is where the story takes its most profound turn. For billions of years, gravity was the undisputed master of the cosmic web, pulling matter together, weaving the filaments, and building the clusters. But as the universe has aged and grown more diffuse, a counterforce has risen to dominance: dark energy. Think of dark energy as a kind of anti-gravity, a repulsive force woven into the fabric of space itself that causes the expansion of the universe to speed up. This changes everything for the web's future. As dark energy accelerates the expansion, the vast distances between the great walls and filaments will stretch even further. The delicate threads of the web will be pulled taut, then begin to grow more tenuous. The flow of gas along them will slow to a trickle, and eventually it may stop altogether. Galaxies will become isolated, their star formation ceasing as their fuel lines are cut by the ever-widening gaps. The universe will grow quieter, colder, and more lonely. The map we are painstakingly assembling today, with its brilliant clusters and glowing filaments, is therefore just a single frame in a film that spans tens of billions of years. We are witnessing the cosmic web in its prime, a vibrant, interconnected era where gravity's work is still visible and ongoing. But the script for the final acts is being written by dark energy, a mysterious force we can measure only by its colossal effects. This means that to truly understand the fate of the web, and by extension the fate of every galaxy within it, we must finally confront this greatest of cosmic mysteries. What is dark energy, and why does it hold the ultimate power over the architecture of everything? Gravity built the cosmic web, but it will not dictate its final chapter. A far stranger force, one we cannot see or touch, holds that power. This is dark energy, a mysterious presence that makes up about 70% of everything in the cosmos. Its nature is unknown, but its effect is unmistakable. It is causing the expansion of the universe to accelerate, to speed up over time. For billions of years, gravity worked diligently against this steady expansion, pulling matter together to weave the great filaments and clusters. It was a close contest, a delicate balance. But roughly 5 billion years ago, a tipping point was reached. The universe had grown so large and diffuse that dark energy's repulsive push began to overwhelm gravity's local pull. Imagine a great ship trying to sail against a strengthening tide. For a while, the ship's engine's gravity could make headway, but as the tide, dark energy, grows ever stronger, forward progress becomes impossible, and the ship begins to be swept backward. This is the transition our universe is undergoing. We are living in the unique era where we can still see gravity's magnificent handiwork, the glittering web in all its connected glory, while also measuring the force that will ultimately unravel it. This makes our present moment a precious window in cosmic time. We are like historians arriving at the peak of a great civilization, able to study its bustling cities and trade routes just as a distant storm appears on the horizon. Dark energy's influence on the web is profound and growing. Its acceleration stretches the very fabric of space between the great structures. As the distances between filaments and superclusters grow, the gentle gravitational tugs that still connect them become weaker, stretched thin across the widening gulf. The cosmic web is not being torn apart violently. Instead, it is being pulled into a state of profound isolation. The flow of gas along the filaments, the lifeblood of galaxies, will gradually slow to a halt as the gravitational gradients that drive it flatten out. New large-scale structure will cease to form. Superclusters like our own Laniakea, which are still in the process of collapsing under their own gravity, may never fully coalesce. Dark energy acts as a cosmic brake, preventing their final merger. The great attractors of the future will find their pull is no longer strong enough to overcome the accelerating space between them. Looking far ahead, the fate dark energy writes is one of increasing solitude. Galaxies that are not already bound in tight, local groups will be carried apart by the stretching space. Their light will redshift into invisibility. The brilliant nodes of the web will fade as their stars age and new stars are no longer born. The universe will grow colder, darker, and more silent. The intricate architecture we are mapping today, the vast walls and delicate threads, will be stretched beyond recognition, a ghostly pattern fading into an ever-expanding emptiness. This gives our current investigations a profound urgency and poignancy. We are not just mapping the universe's structure, we are documenting a masterpiece during its brief, vibrant prime, capturing the connected cosmos before the lights begin to go out, one by one, across the vastness of space and time. This realization forces us to confront a deep and ancient human fear, the terror of cosmic loneliness. For centuries, we have gazed up at the silent, dark spaces between the stars and felt a profound isolation. Our planet seemed a fragile, solitary outpost in an indifferent and endless void. The cosmic web shatters that illusion completely. The emptiness is not the default state of the universe. It is the necessary contrast that defines a magnificent, pervasive connection. We are not adrift in a formless sea. We are embedded within the largest, most intricate structure known to exist, a single organism of matter and gravity spanning tens of billions of light years. Every atom in our bodies was forged in stars that themselves formed from gas flowing along these ancient filaments. We are not just living in the universe. We are literal extensions of its architecture, conscious nodes in a network of staggering scale. This connection is not mystical but physical, written into the very laws that govern reality. From the quantum ripples of the first instant to the grand walls we map today, a single set of principles of gravity and motion has orchestrated this entire symphony. The universe began in a state of near-perfect uniformity, a blank canvas. Through the patient, algorithmic work of physics, itself organized, it transformed that initial simplicity into the breathtaking complexity of the web, of galaxies, of planets, and of life. This reveals a cosmos that is fundamentally creative, a system that generates order and structure as naturally as it expands. Our existence here is not a random accident against impossible odds. It is a direct, if incredibly distant, consequence of that creative impulse. We are the universe becoming aware of itself, looking back along the filament that birthed us and tracing our lineage to the dawn of time. This perspective does not diminish us, it redefines our role. We are not passive bystanders on a tiny rock. We are active participants in an unfolding story of cosmic evolution. Our quest to understand the web, to map its filaments and decipher its history, is the universe using its own creation, the human mind, to comprehend its own grandeur. When we point our telescopes into the depths, we are not outsiders looking in. We are the cosmos looking at itself, beginning to understand the beautiful, invisible threads that bind everything together into one coherent, astonishing whole. The intricate patterns of the cosmic web are more than a beautiful map. They are a cosmic fingerprint, a unique signature left by the fundamental laws of physics themselves. This is the sixth principle, the web as a cosmological probe. The precise way galaxies cluster, the exact diameters of the vast voids, and the statistical thickness of the filaments are not random artistic choices. They are the direct, measurable outcome of a specific recipe for the universe, a recipe defined by the amounts of dark matter and dark energy, the behavior of gravity on the largest scales, and even the subtle influence of the most ghostly known particles, neutrinos. Think of it like this: if you shake a tray filled with sand, the patterns that form will depend entirely on the size of the grains, the force of your shake, and the friction of the tray. By studying the final pattern, you can deduce the properties of the system that created it. The cosmic web is that final pattern, but the tray is the entire observable universe, and the shake was the Big Bang. Every cosmological model, every theory about what dark energy is or how dark matter behaves, makes a specific prediction for what the web should look like today. A universe with more dark energy, for instance, would have started its accelerated expansion earlier. This would have put the brakes on structure formation sooner, resulting in a web that is less tightly knit, with thinner filaments and larger voids. A universe where dark matter particles are warmer, meaning they move faster, would smooth out the smallest wrinkles in the early universe. This would erase the tiniest filaments and dwarf galaxies, leaving behind a web that is more coarse-grained. Even neutrinos, which stream almost freely through the cosmos, have a measurable effect. Their tiny mass and high speed allow them to wash out some of the very fine-scale clustering of matter, subtly changing the statistical distribution of galaxies. By creating exquisitely detailed three-dimensional maps of billions of galaxies, projects like the upcoming Vera Rubin Observatory and the Euclid Space Telescope are essentially taking a high-resolution scan of this cosmic fingerprint. They are not just counting galaxies, they are measuring their precise positions in three-dimensional space to a degree of accuracy that was unimaginable a generation ago. Astronomers then compare this immense, real-world dataset against millions of sophisticated computer simulations. Each simulation represents a slightly different universe, with different values for dark energy, different types of dark matter, or different theories of gravity. The simulation whose virtual cosmic web most closely matches the one we actually observe wins. It tells us which recipe of ingredients and physical laws best describes our reality. This transforms the cosmos from a place we simply observe into the ultimate laboratory. We are using the universe itself, in all its 14 billion-year complexity, as an experimental apparatus to test physics at energies and scales far beyond anything we could ever recreate on Earth. The silent, glittering architecture above us is not just a spectacle, it is the most precise instrument we have for listening to the whispers of creation. This grand map of the cosmos is being drawn by more than just telescopes and supercomputers. It is a project that invites the entire world to participate. For over a decade, a remarkable online platform called Galaxies has harnessed the power of human curiosity to tackle a task too vast for any single research team. It presents volunteers with stunning images of galaxies captured by robotic surveys and asks a simple question: is this galaxy a spiral or an ellipse? With a few clicks, anyone can help classify these distant islands of stars. This might sound like a small contribution, but it is monumental in scale. The human brain possesses an exceptional, intuitive ability to recognize patterns and subtle details that even sophisticated algorithms can miss. Millions of classifications from hundreds of thousands of volunteers have created an immense crowd-sourced catalog, helping astronomers understand how galaxies are distributed and how their shapes correlate with their position in the cosmic web. This is citizen science at its best, turning a global community into a single, distributed research instrument. The collaboration does not stop there. Major observatories like the Hubble Space Telescope and the Sloan Digital Sky Survey have long-standing policies of releasing their raw data to the public after a proprietary period. This means the same breathtaking images and intricate spectra used by professional astronomers are available for anyone to download, process, and explore. Amateur astrophotographers create stunning visualizations from this data, while students and hobbyists can hunt for unusual galaxies or trace faint structures. This open access philosophy democratizes discovery. It acknowledges that a brilliant insight can come from anywhere, from a retired teacher in Lisbon to a high school student in Tokyo. When you look at a publicly released image of a distant galaxy cluster, you are seeing the same light, the same photons that traveled for billions of years, that a professor at a major university is analyzing. This shared access creates a profound connection. It transforms the cosmic web from an abstract concept studied by a distant elite into a shared human heritage that we are all helping to chart. The quest to understand the universe's largest structure becomes a collective journey, reminding us that science is not a walled garden of knowledge, but an open field where curiosity is the only required ticket. Our current map of the cosmic web is a breathtaking achievement, yet it remains a sketch of a continent we have only glimpsed from the shore. Every line we draw is constrained by two fundamental limits: the edge of what we can see and the resolution of our instruments. The observable universe is a sphere centered on us, defined by the finite distance light has had time to travel since the Big Bang. We cannot map what lies beyond that cosmological horizon, and we have no reason to believe our local web is special. The grand architecture likely continues in similar patterns far into the unobservable vastness, perhaps with variations we can never detect. Even within our viewable realm, our telescopes have a resolution limit. We can trace the thick, luminous trunks of the great filaments, but the finer capillaries, the delicate strands where gas first begins its gravitational journey, remain below our current threshold of sight. It is like viewing a sprawling forest from an airplane window. You see the major groves and clearings, but you miss the intricate root systems connecting every single tree. This means our understanding of the web's most vital processes is still theoretical. We have models for how gas cools and condenses within these filaments to fuel galaxies, but observing that transformation directly in real time is a monumental challenge. The physics is complex, involving turbulence, magnetic fields, and shock waves on scales that are incredibly difficult to simulate with perfect accuracy. Does the gas flow smoothly like a river, or does it arrive in clumps and spurts? How exactly does it shed its heat to collapse into stars? These are open questions at the very heart of galactic growth. Furthermore, cosmologists wonder about the web's true geometry. Is it simply a random cosmic foam, or could its pattern contain subtle topological clues about the overall shape of the universe itself? Could the way filaments connect and voids align hint that space is curved on the absolute largest scales, perhaps even folding back on itself in some higher dimension? These are not idle speculations. They are active frontiers of research, driven by the next generation of telescopes and sky surveys. Each new, deeper map will push these boundaries, revealing finer details and potentially uncovering structures so vast they make our current superclusters look like neighborhoods. This incompleteness is not a failure. It is the engine of discovery. the most exciting realization is that the majestic cosmic web we have just spent this journey exploring is almost certainly just the first draft of a much richer, more astonishing story waiting to be read. The most profound truths of the cosmos often require a bridge, a way to translate the language of mathematics and light into something our human minds can truly feel. To grasp the cosmic web, we must move beyond charts and simulations and find analogies that resonate in our own world. One of the most powerful comparisons is to the human brain. Envision the cosmic web as a neural network on the grandest possible scale. In this analogy, each galaxy is like a neuron, a cell of luminous activity. The dark matter filaments are the axons, the long, slender pathways that connect these neurons, transmitting not electrical signals, but the fundamental force of gravity. The dense clusters where filaments intersect are the brain's major hubs, like the thalamus or cortex, where processing and integration occur on a staggering level. Just as thoughts and memories emerge from the silent, invisible connections between neurons, the entire dynamic story of the universe, its evolution and structure, emerges from the gravitational dialogue flowing along these dark threads. It is a reminder that the same principles of connectivity and network organization appear in nature at vastly different scales, from the 3 pounds of tissue in our skulls to the observable universe itself. For a different perspective, picture the universe as a colossal, cosmic sponge. This sponge is not solid. It is mostly empty space defined by a delicate lattice of material. The filaments of the cosmic web are the solid, porous framework of the sponge itself, the intricate matrix that gives it shape and strength. The voids, those immense spherical regions of near-nothingness, are the air pockets and holes within the sponge. They are not mere accidents, they are essential structural components. Without these voids, the sponge would be a dense, formless block. It is the interplay between the solid lattice and the empty spaces that creates the sponge's useful, resilient form. In the same way, the majesty and definition of the cosmic web's great walls and filaments rely entirely on the contrasting emptiness of the voids that border and compress them. The universe is not a solid mass. It is a frothy, structured foam where most of the volume is defined by what is not there. Perhaps the most organic metaphor comes from beneath our feet, in the hidden world of a forest. Beneath the soil, vast fungal networks known as Mycelium connect the roots of trees over enormous areas. This wood wide web, as scientists call it, is a symbiotic communication and resource-sharing system. A tree in a sunny spot can send nutrients through the fungal threads to a seedling struggling in the shade. A tree under attack by pests can send chemical warnings to its neighbors through this underground network. The cosmic web functions in a strangely similar way. The filaments are the mycelial threads, and the galaxies are the individual trees. While they do not communicate in a biological sense, they are physically linked by the gravitational influence flowing through the dark matter pathways. Resources in the form of primordial gas are distributed along these channels. The fate of a galaxy is intimately tied to its connection to this larger network, just as the health of a tree is influenced by its place in the forest's hidden web. These analogies are not perfect scientific descriptions, but they are vital tools. They transform the cosmic web from an abstract, distant concept into a pattern we recognize, a structure that feels alive, interconnected, and strangely familiar. They help us internalize the breathtaking idea that we are not just in the universe, but of it, participants in a network of relationships that spans from the fungal threads in the soil to the gravitational threads between the stars. The same pattern that captivates scientists has begun to ignite the imaginations of artists around the world. This is where raw data transforms into profound beauty, where the cold mathematics of cosmology meets the warmth of human creativity. Across digital canvases, artists are using the actual outputs from supercomputer simulations as their starting point. They take the three-dimensional maps of dark matter, the intricate traceries of filaments and nodes, and they infuse them with color, light, and motion. What emerges are not mere illustrations, but breathtaking visual symphonies, vast tapestries of golden threads against deep cosmic blacks, swirling nebulae cradled in sapphire filaments, or minimalist renderings that highlight the web's elegant geometry. These works do something a graph cannot. They allow us to feel the scale and the sublime intricacy of the structure we are part of. They are a translation from the language of physics into the language of emotion, making the invisible architecture not just comprehensible, but visceral and awe-inspiring. This artistic impulse to map connection is not new. It echoes through our oldest stories. Many mythologies speak of a world tree, an axis connecting the heavens, the earth, and the underworld. Others describe a cosmic weave, a tapestry spun by goddesses where every thread is a fate or a star. These ancient motifs and the modern cosmic web are born from the same human longing to find order and relationship in the vast unknown. They are narratives that reject the idea of a chaotic, indifferent universe, insisting instead that everything is interwoven into a meaningful whole. Philosophers, too, have long pondered the concept of the great chain of being, or the interconnectedness of all things. Today, science is providing a tangible, observable framework for that profound intuition. The filaments are the physical manifestation of that ancient dream of connection. This resonance powerfully fuels modern storytelling, especially in science fiction. Narratives of galactic empires linked by web-like transit networks, or of ancient, universe-spanning structures left by vanished progenitors, directly channel the awe of the cosmic web. They explore the implications of living inside a truly connected cosmos. Would such a structure imply a creator, a cosmic architect, or does it demonstrate a self-organizing principle, a universe that naturally weaves itself into complexity? These stories use the web's architecture to ask deep questions about purpose, destiny, and our place within a grand design. They remind us that science does not erase mystery, it simply gives that mystery a new and more magnificent shape. When a musician composes a piece based on the fractal patterns of the web, or a poet writes of galactic rivers, they are participating in a timeless dialogue. They are using the vocabulary of our era, the vocabulary of astrophysics, to continue the human project of meaning-making. This cultural dimension reveals something essential. The cosmic web is more than a scientific model. It is a modern mythos, a source of symbols and stories that help us navigate our own existence within an unimaginably large and ancient universe. It satisfies a deep need to see not just stars but constellations, not just galaxies but a grand design. In blending art and science, we do not diminish the facts. We illuminate them, allowing the truth of our connected cosmos to resonate not just in our minds but in our hearts. The same elegant pattern of filaments and nodes repeats itself throughout the natural world, as if the universe has a favorite blueprint. Look at a satellite image of a great river delta, its main channel fracturing into countless smaller tributaries that reach into the land. Examine the silhouette of a tree, its trunk dividing into branches, then twigs in a fractal cascade. Even the lightning bolt that splits the sky follows this branching, efficient path of least resistance. These are not mere visual coincidences. They are manifestations of a profound principle that seems to govern how complex systems organize themselves, from the flow of water to the flow of information. The cosmic web is the ultimate expression of this principle, operating on the grandest possible stage. This is the seventh principle, the stunning interconnectivity across all scales. A growing field of science known as network theory studies these patterns. It finds that whether you are mapping neurons in a brain, users on a social media platform, or galaxies in a supercluster, the underlying architecture often obeys similar mathematical rules. These systems tend to form what are called scale-free networks. In such a network, most points have only a few connections, but a few critical hubs have a vast number of links. Think of an airport system. Many small regional airports connect to a few major international hubs. Or consider the Internet, where countless personal devices connect through major servers and data centers. The cosmic web is a perfect, three-dimensional example of this. Countless smaller galaxies reside along filaments, but the massive galaxy clusters at the intersections act as the gravitational hubs, anchoring the entire local structure. This organizational logic emerges because it is efficient. It is the optimal way to move resources, whether that resource is water, electrical signals, digital packets, or intergalactic gas, through a complex system with the least amount of energy and the greatest resilience. A river delta forms its branches to most effectively distribute sediment and water. A tree grows its canopy to maximize sunlight capture. The cosmic web formed its filaments to channel matter under the relentless pull of gravity. The universe, it seems, is not just creative but economical. It finds and reuses successful patterns. This repetition hints at something deeper than analogy. It suggests there may be fundamental, universal laws of organization that transcend the specific details of physics or biology. These are mathematical principles that describe how connectivity arises from competition and cooperation, how local interactions give rise to global structure. When we look up at the web of galaxies, we are not just seeing astronomy. We are seeing a case study in a universal tendency for matter and information to self-organize into networks. This realization bridges the chasm between the human scale and the cosmic. The same logic that shaped the community you live in, with its roads converging on town centers, also shaped the community of galaxies we inhabit. It is a humbling and unifying thought. Our quest to understand the cosmos has led us to a mirror, reflecting back a pattern so fundamental it seems woven into the fabric of reality itself. The universe's grandest map is about to be redrawn in breathtaking detail. Our current understanding of the cosmic web, as magnificent as it is, remains a sketch based on millions of galaxies. The next generation of observatories will chart billions, transforming that sketch into a dynamic, three-dimensional atlas of almost unimaginable precision. These are not just bigger telescopes, they are entirely new kinds of eyes, designed to see the invisible threads of the web in ways we never could before, revealing not just its shape but its motion and history. Leading this charge is the Euclid Space Telescope, a mission dedicated to one profound question: what is the nature of dark energy and dark matter? Euclid will peer across 10 billion light-years of cosmic history, measuring the precise shapes and redshifts of over 1 billion galaxies. But it is not just cataloging them. It is using a phenomenon called weak gravitational lensing. As light from distant galaxies travels toward us, it is subtly distorted, warped by the gravitational pull of all the dark and ordinary matter it passes through, including the vast filaments of the cosmic web. By analyzing the tiny, systematic twists in the shapes of billions of galaxies, Euclid will trace the distribution of dark matter directly. It will create the most extensive mass map of the universe ever made, showing us the web's dark skeleton in unprecedented detail, and measuring how its structure has evolved over cosmic time to unravel dark energy's influence. While Euclid maps the dark matter scaffold, another colossal project will map the web's luminous gas. The Square Kilometre Array, or SCAR, is not a single dish but a revolutionary network of thousands of radio antennas spread across 2 continents. Its primary target is the faint radio whisper of neutral hydrogen, the most abundant element in the cosmos. This hydrogen traces the warm-hot intergalactic medium, the WHIM, that flows through the filaments. The SKA's incredible sensitivity will allow it to detect this signal across billions of light-years, creating a 3-dimensional map of the cosmic web's gaseous content throughout the universe's history. We will see how these rivers of fuel have changed over time, where they flow fastest, and how they feed galaxies at different epochs. Together, Euclid and the SKA represent a quantum leap. They will move us from static maps to a living, breathing model. We will not just see where the filaments are. We will see how matter moves within them, how the web has grown from the first thin threads to the great walls of the modern cosmos, and how dark energy is now stretching it thin. This is the difference between a single photograph of a forest and a continuous, high-definition film showing every tree's growth, every season's change, and every animal's path through the understory. The cosmic web is about to come alive before our eyes, and with this new vision, we will confront mysteries we have not even yet begun to imagine. The invisible filaments that shape galaxies may also hold the key to life itself. This is not a claim that life exists on the dark matter threads, but a profound recognition that the cosmic web sets the stage for life's potential. For life as we understand it, you need more than just a star and a planet in the right zone. You need a rich chemistry, a periodic table filled with elements like carbon, oxygen, iron, and silicon. These elements are not primordial. They were forged in the hearts of stars and scattered into space by stellar explosions. This is where the web's dynamic flow becomes essential. The filaments act as the universe's great circulatory system. When a massive star dies in a supernova, it enriches the surrounding gas with these newly created heavy elements. That enriched gas does not simply sit still. It is caught in the gravitational currents of the web, funneled along the filaments like nutrients in a bloodstream. Over billions of years, these life-giving elements are distributed from their stellar forges out into the broader galactic environment. They travel along these dark highways, eventually reaching the quieter spiral arms where new stars and planetary systems form. A solar system born from gas enriched by countless prior stellar generations inherits the full chemical toolkit for building rocky planets, complex molecules, and perhaps life. In this way, the web does not create life, but it enables the conditions for life's chemistry by ensuring that the products of stellar alchemy are not trapped locally, but shared across immense cosmic distances. It suggests that truly isolated galaxies cut off from the web's nourishing flows might be chemical deserts, poor in the very ingredients that make biology possible. Our own solar system, with its abundance of heavy elements, is likely a beneficiary of this ancient, large-scale distribution network. We are, in a very literal sense, children of both the stars and the streams that connected them. This cosmic connectivity invites us to think bigger about the search for life. If technological civilizations arise, their perspective would be fundamentally shaped by understanding this architecture. For a spacefaring species, the filaments are not just lines on a map. They are the gravitational geography of their galaxy and beyond. Navigating between stars efficiently would mean using these channels, following the natural contours of spacetime where propulsion energy could be minimized. The web could define the routes of future exploration, the intergalactic trade winds that guide voyages. Even more speculatively, if a civilization sought to communicate across galactic distances, they might look to the web itself. The dense clusters at the nodes, or perhaps even the stable gravitational points along the filaments, could serve as natural amplifiers or relay stations for signals, turning the universe's largest structure into a potential communications network. While this remains in the realm of thoughtful speculation, it powerfully reframes one of humanity's oldest questions. The search for extraterrestrial intelligence is not just about pointing telescopes at random stars. It is about understanding the cosmic neighborhood, its infrastructure, and the flows of matter and information that might connect one island of life to another. We are learning to read the street signs of the universe, written in gravity and starlight, and in doing so, we are beginning to ask if we are truly alone in a silent web, or simply waiting to hear a signal travel along one of its ancient, luminous threads. That faint, hazy patch of light known as the Andromeda Galaxy is more than a neighbor. It is a fellow traveler on the same local filament, a companion in the slow, gravitational current that guides our Milky Way's journey. This changes everything about a quiet moment under the stars. When you look up, you are no longer simply seeing isolated points of light against a black void. You are witnessing the luminous highlights of an immense three-dimensional structure. The bright star Sirius, the red glow of Betelgeuse, the delicate band of the Milky Way itself, each is a part of a galaxy that is, in turn, a stitch in this grand tapestry. The darkness between them is not mere emptiness, but the profound negative space of a cosmic void, or the deep channel of a filament yet unseen. This realization transforms stargazing from passive wonder into an active act of cosmic cartography. You are not just looking at the sky, you are reading a map of gravitational relationships written across billions of years. You can trace with your mind's eye the invisible lines of force that connect what you see, understanding that the very reason these stars and galaxies are arranged as they are is because of the web's ancient architecture. It allows you to feel, in a deeply personal way, that you are situated within the structure, not outside of it looking in. The awe comes not from distance, but from intimacy, from the profound connection that binds your gaze to the fabric of the cosmos. This perspective is the ultimate gift of our scientific journey, turning the familiar night sky into a window onto the largest story ever told. These 7 principles form the backbone of our cosmic story, a narrative woven from invisible threads. First, gravity, the patient sculptor, used the faintest ripples from the Big Bang to draw the dark matter skeleton, the universe's first and largest structure. Second, ordinary matter, the stuff of stars and planets, was not the architect but a follower, flowing like iron filings along the magnetic field of this dark scaffold. Third, this structure is defined as much by absence as presence, with the immense spherical voids acting as the foundational negative space that gives the luminous filaments their sharp, breathtaking definition. Fourth, a galaxy's destiny, whether it remains a vibrant spiral or becomes a red and dead elliptical, is largely dictated by its address within this architecture, by whether it resides on a quiet filament or in a violent cluster core. Fifth, the web is not a frozen monument but a dynamic, evolving entity, its fate now caught in the tug of war between gravity's enduring pull and dark energy's accelerating push. Sixth, the precise statistical patterns of the web serve as the universe's ultimate laboratory, a cosmological probe letting us test the nature of dark matter, dark energy, and the fundamental laws on scales impossible to replicate on Earth. And seventh, this pattern of filaments and nodes is not unique to cosmology. It echoes in river deltas, neural networks, and fungal mycelium, suggesting a universal principle of efficient, resilient organization. Together, these ideas transform a collection of astronomical facts into a single, coherent epic. They show us a cosmos that is fundamentally creative, self-organizing from a near-uniform beginning into an intricate, connected whole. The cosmic web is the framework that ties the history of the first stars to the motion of our own galaxy, and the nature of ghostly particles to the potential for life itself. It is the story of how our universe built itself, from the quantum whispers of the first instant to the grand, glittering tapestry we map today. This journey through the cosmic web reveals a universe of breathtaking connection. We have traveled from the invisible threads of dark matter that first sketched the blueprint, to the luminous galaxies strung along them like pearls, and onward to the vast, spherical voids that give the entire structure its form. This is not merely a map of where things are, it is the true, dynamic architecture of reality itself, governing the birth, life, and ultimate fate of every galaxy, including our own Milky Way. It challenges a deep, ancient perception of cosmic isolation, replacing it with a profound vision of a single, coherent organism woven together by the elegant and patient laws of physics. These laws took the faintest whispers of quantum fluctuation and spun them over billions of years into the grand design we are only now beginning to trace. Our place within this network is not accidental. It is a direct consequence of that creative impulse, a thread in the tapestry. As our telescopes grow more powerful and our maps more detailed, remember this: you are not a distant spectator gazing at an alien realm. You are a participant embedded within the largest structure known to exist. Every atom within you was forged in a star that itself formed from gas flowing along these ancient filaments. To look up at the night sky now is to look out along the branching pathways of home. If this vision of a connected cosmos has reshaped your perspective, we would love to hear your thoughts in the comments below. For more journeys to the heart of space's greatest mysteries, subscribe and join us as we continue to explore. And the next time you stand under the stars, look up and remember, you are seeing the universe not as a scattering of lonely lights, but as one magnificent, interconnected whole.